Okay. Good morning. So we are starting today the lecture 26 and continuing our the same topic MOS, metal oxide semiconductor devices. In the last class you remember we defined the MOS device as a diode or a capacitor like this, which is a semiconductor of P-type or N-type. In this case we assume P-type silicon on which is very good quality oxide or any insulator film of very high resistivity and breakdown voltage called insulation properties. And then we have a gate electrode, a metallic or as I said, polysilicon electrode, and that forms a metal oxide semiconductor diode or capacitor. And we have seen when we use a P-type silicon substrate and we consider an assumption which is called flat band approximation, then we have seen that when Vg is equal to 0 with respect to the substrate, then the energy band of silicon goes flat up to the interface without any bending. That is what is called flat band approximation. Then if you apply a positive gate bias, the majority carriers are repelled, whereas minority carriers are attracted, and up to a voltage Vi for which the energy band bending at the surface, which is called surface potential, is equal to phi f. Phi f is the Fermi potential as measured from the intrinsic Fermi level. And when the phi s, the surface potential, is equal to that phi f, we say that the surface behaves as an intrinsic surface. And up to that point we call it pure depletion. As soon as Vg exceeds that Vi, the condition for which phi s is equal to phi f, we say that the surface enters into the weak inversion or subthreshold region. Then what happens? The depletion layer which gradually expands in thickness, and more minority carriers, in this case electrons, they accumulate at the surface. And when you create a situation when phi s is equal to twice phi f, we say the surface is inverted at the threshold of inversion. That means then at that point the electron density, the minority carrier density at the surface is equal to the majority carrier density at the bulk region, in the bulk region. And we say this voltage Vg, which we call threshold voltage, we say that that your diode is just at the onset of threshold, at the onset of inversion. At that point above, that is when you apply a voltage which is much more than that Vt which we defined earlier, threshold voltage, then the surface becomes strongly inverted. When surface becomes strongly inverted, then within a very thin layer, about 100 angstrom thickness, lot of electrons accumulate. Lot of electrons. These electrons are opposite to the majority carriers in polarity, so they are called inversion layer, because it is now the charge of those electrons is just in the inverted form of the charge contributed by the majority carriers in the substrate. That's why the name inversion layer. When inversion layer is formed, the device is usually, say, if you form a device having 2n plus at two ends of the gate, which is called MOSFET, okay, then we say the device becomes on. Afterward, we derived an expression for the total charge density at the surface. The charge density at the surface. We derive an expression for the charge density at the surface, and we saw how that charge density gradually changes with the surface potential. Again, surface potential being a function of the applied gate bias. Generally, under flat band approximation, when Vg is negative, surface potential is also negative. When Vg is 0, psi s is equal to 0. And when Vg is positive, psi is also increases positively. Okay. As you remember, I told you that when psi s is negative, that means for negative applied bias, the electrons are the holes, the majority carriers are attracted, and that helps in the formation of accumulation layer. Accumulation layer means the same type of carriers but enhanced in density. The substrate is p-type, means holes, they are dominated by holes. Now at the surface we have more holes than in the bulk, and that is normally limited within a very small thickness, and we call it accumulation layer. And the particular condition of the semiconductor surface is known as accumulation condition. And then, as I explained in the last class through certain derivations, steps of derivation, that gradually not gradually, in fact, the QS increases with the negative voltage or psi s quite rapidly, following an exponential rule, which is exponential psi s by 2 VTH. As we apply a positive bias up to a point for which psi s is twice phi f, the increase is not that rapid. The increase is roughly proportional to the square root of the surface potential. Thereafter, as you cross this point, we call it the onset of inversion, and the corresponding gate voltage is called threshold voltage, and the corresponding psi s is equal to twice phi f. Beyond that, again, the inversion density, the charge density at the inversion layer increase very rapidly, following the same same exponential rule as we have discussed in the last class. In the last class, in the last lecture, you remember that we derived an expression for electric field at the surface. We derived an expression for the charge induced in the surface per unit area. We also derived expressions for the hole density per unit area and electron density per excess hole density and excess electron density per unit area in the surface. We derived those expressions. And ultimately at the end, we derived by differentiating that QS expression with respect to psi s, the surface potential, we got a capacitance expression which looks like this, where the function f was already defined. The exponential, this consists of exponential terms containing e to the power, that psi s divided by VTH divided by 2 VTH plus minus etc. As you remember. And then CD, what is it called? It's called dynamic surface capacitance. Dynamic surface capacitance per unit area. Again, everything per unit area. That is why the unit is farad per centimeter square. Okay. So this expression we derived, and you can calculate the value of CD for different values of psi s straightforward using this equation. There is absolutely no problem for you. And then at flat band, when Vg is equal to 0 and I assume psi s is equal to 0, called flat band approximation, under that flat band condition, CDFB is obtained by putting psi, but if you just make psi s equal to 0, then this equation gives you a 0 by 0 form, which you cannot compute. So you have to calculate the value of CDFB. It's called dynamic condition under flat band condition, when psi s tends to 0 from the positive values. Okay, that is why 0 plus. Then this expression leads to a very simple equation, which is epsilon s by LD. And epsilon by s by LD is something like a depletion capacitance, where depletion layer thickness is LD. This expression looks very similar to the depletion layer capacitance of a PN junction diode, where in W, the depletion layer thickness or weight is replaced here by LD. LD is called the Debye length, and therefore CDFB, which appears to be 0, which should be infinity in fact, when you make Vg is equal to 0, the surface energy band goes straight up to the interface, flat band condition. Then there is no reason why There should not be no question of a capacitance. Capacitance means the capacitance thickness is 0 in that case. Apparently, it will assume it comes like this, that its CD should be infinity, because at the depletion layer thickness decreases gradually, the capacitance increases. So for a value, finite value of Vg, the depletion layer thickness is finite. There is a capacitance CdFb, which is this. Okay, and then as you are gradually decreasing that Vg, the depletion layer thickness decreases, the capacitance should increase. And when you make Vg is equal to 0, when psi s becomes 0, then CD should become infinity. But that does not happen. It leads to a very high value, whose value is not infinity, but a very high value, which is equal to epsilon s by LD. This is normally called the depletion layer, that is called depletion layer capacitance or dynamic capacitance of the semiconductor surface under flat band condition. Dynamic capacitance of the semiconductor surface in MOS capacity under flat band condition. So up to this we discussed in the last class, in the last lecture. Now, if you consider this a total MOS capacitor once again with an applied bias, the different diagrams concerned look like this. For example, you consider the metal, silicon dioxide, and p-silicon MOS. Then suppose this is your vacuum level, this is your Fermi level in the metal, so that this is what is called phi m, which has been lowered, and this is suppose the original Fermi level when there is no bias applied. And as a result, you remember, which I explained clearly in the last class, that a situation like this will result this is the Fermi level of the p-type semiconductor, and something like will be the EC of the insulator, and somewhere here will be the EV of the insulator. We shall discuss what will exactly happen in the insulator later. For simplicity, let us draw it like this and let us not question on it, how exactly it is shaped, etc. Let us assume that EC and EV, the band will bend linearly, and this is the conduction band of the insulator, bandage of the insulator, and this is the valence bandage of the insulator. Then with the application of, this is not actually this is not phi m, this is my Vg, Q into Vg, Q into Vg. So here this is your Q into Vg. When you apply a bias Vg, which is positive with respect to the substrate, the Fermi level in the metal is lowered by the amount QVg with respect to that of the bulk. So the same within the semiconductor Fermi level will be continuous, because no current, practically no current is flowing. Within the metal, the Fermi level will be horizontal, because we assume that metal is an almost a, that is a equipotential material. And then, of course, within the oxide, there will be a constant field, and as a result, normally we assume that the energy band will bend linearly, as indicated here. And as a result, what has happened? When the valence bandage has been bent downward, same thing for the conduction. So overall band gap, overall energy band has stooped downward to the interface. It is a standard thing. But as a result, what has happened to the space charge density? What will happen to the space charge density? You see that up to this there is a depletion layer. Okay? And this depletion layer means electrons and holes are removed, and this is p-type means there are negative acceptor ions. So in over this region there will be a constant, that is the definition of your depletion layer. So there will be this number, this is I am plotting the rho, the space charge density versus distance. So over this region, this value is nothing but minus QNA. At the interface, here there may be some good number of electrons, depending on how much applied, how much positive voltage you applied. If that positive voltage is equal to or above the threshold voltage which we defined earlier, then there will be a lot of electrons here. And that will also create some extra, these are excess electrons, some space charge, and that is defined like this. So the negative space charge in the semiconductor side will look like this. This is due to the unmasked negative ions over the depletion layer, and this is due to the inversion electrons. I can kindly call it minus Q into Ni. Ni is the average electron density of the inversion layer, roughly. This will not be a constant value, but let us roughly assume that Ni is the average electron density in the inversion layer. Similarly, in the metal side, there will be some charge accumulated at the electrode interface, and that will be something like this, and that must be positive. Is it not? That must be positive. And this may be Qm. And you know that Qm must be equal to Qna plus Qni. In terms of multiplied by, actually it is Qna multiplied by W, the thickness. So it is Qna W into Qna, and this is Qni multiplied by the thickness of the inversion layer. Let us assume that the inversion layer thickness is Wi. So the space charge neutrality will give the total amount of space charge over the positive electrode at the interface between the metal and the oxide will be equal to the total negative charge at the interface and at the depletion layer taken together. This is due to the charge neutrality, space charge neutrality to any condenser. The total positive charge accumulated in the positive plate should be equal to the total negative charge accumulated at the negative plate. That will happen. The electric field over this region, if I plot the electric field, is a plot of space charge density, space charge density versus X. So it's the space charge density distribution over a MOS capacitor, and this is the electric field distribution. Electric field as a function of X, again as a function of X. Then how the electric field will look like? Within the metal, the electric field should be 0. Within the metal, the electric field must be 0. Then within the oxide, the electric field may be a constant value as indicated here by a linear slope. And then within the depletion layer, electric field may be usually constant, usually linearly varying, so that this is your W, the depletion layer width. And the electric field, this electric field I call electric field at the insulator, and this electric field I call electric field in the semiconductor at X is equal to 0. And you know, electric field will be discontinuous, but the electric displacement will be continuous. So epsilon I multiplied by capital epsilon I is the electric field, is a displacement in the insulator, will be equal to the epsilon S0 multiplied by epsilon cap small epsilon s. That means electric field at the semiconductor in the interface, in the semiconductor at the interface, multiplied by the dielectric constant of the semiconductor. That means electric displacement vector will be continuous. Normal, that is one of the boundary conditions between the two dielectrics. The electric displacement, normal component of electric displacement is continuous, whereas tangential component of the electric field is continuous, electric flux density is continuous. And similar way, I can plot the potential. This is, please note that this is SiO2, this is metal, and this is P silicon. Same way, I can plot the potential. Displays the zero. Is a plot of potential against distance. So it is expected that it will be like this. It will be like this. Then it will be like this. Okay? This potential is nothing but my VG, the applied voltage. This is the applied voltage. And this side is grounded. So this side is grounded means potential is zero. Then this potential is called, what is it called? The potential at the surface with respect to the bulk, which is nothing but my surface potential. This potential at the surface with respect to bulk is surface potential, and this potential over the dielectric, over the insulator. Electric field constant means potential variation over the oxide is linear. Del psi del x is electric field. The electric field constant means epsilon should be linearly dependent on x. So that is what is shown. And then this voltage is called Vi. So the total applied voltage Vg at the gate with respect to the substrate is a sum of two components. One is a voltage across the insulator, and the other is the voltage across the semiconductor surface. That is the potential at the surface with respect to the bulk, which is called the surface potential. It's a very, very important question, a very, very important equation. You see that the voltage which is applied at the MOS gate with respect to the substrate is a sum of two components. One voltage which is across the oxide or insulator, which I call Vi. The other voltage which is across the semiconductor surface, that is semiconductor induced depletion layer just below the semiconductor surface, and that voltage is called surface potential. So Vg is the sum of the insulator voltage and the surface potential. This is a very important equation for MOS. Now, as I told you earlier, this Qm, the metal, the charge at the metal side, I write it now as Qn plus so this is the charge at the metal, and Qn is the inversion charge. And that is the depletion layer charge. In this equation, the Qn was written as Qniwi. So that Qn can also be written as Qni average into Wi. Wi then is the inversion layer thickness. Wi is inversion layer thickness. And Ni is the average electron density in the inversion layer. Okay, and we have already written that gate voltage is the sum of the insulator voltage and the surface potential. And you know that the insulator voltage can be written as epsilon I into di. Okay, what is capital epsilon? What is capital epsilon I? Capital epsilon I is the electric field in the gate insulator, assumed to be constant. This may not be constant, please remember, but I have made this assumption that electric field is constant, and di is the insulator thickness. Okay, so Vg is equal to Vi plus psi s, whereas Vi is equal to capital epsilon I into di, capital epsilon I being the electric field in the insulator. Let us forget about sign. Let us consider, because Vg is positive for NMOS, you remember Vg has to be positive for depletion and inversion to be created. So all these are positive. In the case of PMOS, everything, this is negative, this is negative, this is negative. Please remember this, then there will be absolutely no confusion. For NMOS, means P substrate, Vg, Vi, psi s, they are all numerically positive. Whereas in the case of PMOS, that the substrate is the N-type, Vg, Vi, psi s, they are all numerically negative. So this should be kept in mind. Where Vi is the product of the electric field in the insulator and the thickness of the insulator film, called gate oxide. Sometimes we call it TOX, gate oxide thickness. Then Vi, once again let me write, into di, can be written as this, by applying that Gauss's theorem, this electric field can be written as Qs divided by epsilon I. Okay? The electric charge stored in the insulator is equal to the electric displacement, normal component of the electric displacement, which is equal to epsilon I into capital epsilon I. So simply, and then this multiplied by di. And this can be written as Qs divided by, is it alright? Qs is a surface charge, that means interface charge. So there is a charge at the semiconductor oxide interface. And because of that, there will be electric field on the insulator as well as in the semiconductor. What will be the value of the electric field in the insulator? That Qs divided by epsilon I. What will be the value of the electric field in the semiconductor? Qs divided by epsilon s. Epsilon s is the semiconductor permittivity and epsilon I is the insulator permittivity. Okay? And di is the insulator thickness. And then this can be finally written as this divided by Ci, where Ci is equal to epsilon I divided by di, and that is called insulator capacitance per unit area. Sometimes we call it COX. COX means oxide capacitance per, but in general let us write Ci. because it's not necessary that the insulator should be always oxide. So let us write Ci. Then you see that you note that this Ci is called the insulated capacitance per unit area. Vi therefore is given by this. Now the total MOS capacitance C, if you look at the MOS capacitance properly, this is a MOS capacitance structure. So let me draw it once again here. The basic MOS capacitance looks like this. So this is a metal oxide semiconductor capacitance. An equivalent circuit should be something like this. There is a capacitance contributed by this insulator, and then there is a capacitance contributed by this depletion layer and inversion layer taken together. So you see that the total MOS capacitance can be viewed as to consist of two capacitances in series. One is Ci, the insulator capacitance which I have written here. The other is CD, which I have already derived here. This is the CD, called semiconductor surface capacitance per unit area, or depletion layer capacitance per unit. By depletion, I mean depletion inversion taken together. If a large gate voltage is applied, not only the depletion layer has been created, but also an additional inversion layer has been formed. But however, for small gate voltages, only depletion layer will be appreciably formed, whereas inversion layer can be ignored. So this can be kept in mind. This is a very important thing. So therefore, the total capacitance of the MOS is a series combination of the insulator capacitance and the depletion layer or the dynamic capacitance of the surface, and is therefore given by Ci CD divided by Ci plus CD. This is a very interesting thing. And as I was telling you in the last class or the last lecture, if I perform an experiment, okay, I take such a MOS capacitance, apply a DC bias, and measure the capacitance at different values of DC bias. How can you do that experiment? If I want to suppose this is the device under test, we call it DUT, that is the MOS capacitance. I want to measure the CV characteristics of this MOS capacitance. What is to be done? Basically, how to do this experiment? You do the following. So we applied a voltage, a variable voltage, through a reasonably large series resistance. This resistance should be quite large. It should be still small compared to the MOS resistance, that is leakage resistance of the MOS capacitor. That should be otherwise very large, 100 kilo ohm, 500 kilo ohm. Whereas the MOS capacitance resistance may be several tens of mega ohm. Even if you connect 500 kilo ohm, that is small compared to the MOS capacitance resistance, leakage resistance of the MOS capacitance. Then what you do, you connect a capacitance and then a bridge here. A bridge or Q meter or anything, LCR bridge, for the measurement of capacitance at different values of bias. So what you are doing here, you are applying a DC bias via the resistance, and the voltage here will be practically the voltage you have applied, because the current will be so small that the voltage across R can be neglected. It is almost an ideal capacitance. So what is going to happen? When you apply a voltage here, that voltage and the voltage across the DUT, device under test, in this case MOS capacitance, will be practically the same. This is so far as DC is concerned. But this LCR bridge is an instrument where is based on that Wheatstone bridge or kind of bridge principle. But then this measurement is for AC only. So from this instrument, a small AC voltage comes and is applied across the device under test. So what you are doing? You are applying a DC, and over and above that you are applying a small AC. And that the response to that small AC voltage which is coming, and what is the corresponding current? That is the capacitance. You know that any component, if you apply a delta V across it, the nature of delta IC will tell you what is the component. If delta IC is simply proportional to delta V, it is a pure resistance. However, if I find that it is proportional but there is a phase lag, in one case there is a phase lag, the other case there is a phase lead. In one case there will be capacitance, the other case there will be inductance. Okay, so this LCR bridge also applies across the device under test a small AC voltage, and that is over and above the DC bias what we are applying. So as if what you are doing, you are applying a DC bias which I am calling VG with respect to 0 volt, VG with respect to 0, but over and above that VG you are applying a delta V. This delta V can also be called VAC. So total voltage V as a function of time, is equal to VG plus VAC. Okay, VG, V as a function of time is equal to VG, the DC component of voltage, plus a small AC component. That is my delta V. Is it clear? Under that condition, it is measuring what is the capacitance, and that is standard principle of this. If you do that kind of study, then you can easily measure that capacitance. Before doing that, you do the following. You take this expression. Okay? Ci is constant. Ci is simply given by epsilon I by di. So for the given oxide, given insulator, and for the given thickness of the insulator, Ci is fixed. So many farads per centimeter square. But then CD can be calculated using this equation. CD can be calculated using this equation for different values of psi s, and psi s and Vg are related through this equation. Already derived, psi s and Vg, they are related. Already seen. Vg is equal to Vi plus psi s, whereas Vi is equal to epsilon I di, and epsilon I di is equal to Qs by Ci. So what is Vg? Vg is equal to Qs by Ci plus psi s. We'll be coming to that point afterward. So it is possible to, for a given value of Vg, you can calculate the value of psi s, and for the particular value of psi s, you can calculate CD. So what you can do, you can calculate the value of the total capacitance for different values of applied voltage. You can calculate it using the relations which you have developed. Firstly, use this formula, compute Ci from this, and compute CD from this for different values of Vg. That means for different value of psi s, and plot the curve. You will get a following kind of curve. This is a very interesting curve you'll get. This is the total applied voltage, and this is the measured is a capacitance. This curve which you generate theoretically is called ideal CV plot. This curve which you generate theoretically, the way which I have described just now, is called ideal CV plot. The maximum value here is nothing but Ci. this value, the starting value is Ci, the insulator capacitance per unit. I am considering per unit area, not the total per unit area value. So if I know the value of the area, then you divide all these measurements by area so that you get the capacitance per unit area. Okay, this is very important. What is this capacitance? Can you tell me? What is this capacitance? When V is equal to V means Vg is 0. What is the expected value of capacitance here? When the gate voltage is 0, what should be the capacitance? Should be Ci, isn't it? Because energy band goes flat up to the interface. And the voltage therefore across the insulator is Vi. Whatever voltage you are applying, V, that will totally fall across the insulator. So the capacitance should be the insulator capacitance. But that does not happen because of that flat band capacitance, this thing. So what is this capacitance? It's called flat band capacitance, CFB. This is called CFB. And this CFB is a series combination of Ci and CDFB. So this is all right. Same thing. C is equal to, at every capacitance is a series combination of Ci and the dynamic capacitance, the semiconductor depletion layer capacitance. Okay, so that depletion layer capacitance becomes CDFB under flat band condition when V is equal to 0. So this capacitance will be little bit less than that Ci. This is very, very important. This is very important. And this capacitance is called flat band capacitance. Please note, the capacitance starts decreasing from the maximum value, which is Ci, the insulator capacitance. At flat band, it decreases to CFB, which is called flat band capacitance. Thereafter, the capacitance goes on decreasing. Why it is decreasing? Because the depletion layer is forming and forming and forming. The depletion layer which is increasing. So there is parallel series combination of Ci. Ci is constant. CD is the depletion layer capacitance. It starts from CFB value. When V is equal to 0, CD is equal to CDFB. So the total capacitance is CFB. Okay? But then, as you are increasing Vg, the depletion layer widens, so CD will decrease. The series combination will also decrease, and that is exactly happening. It achieves a minimum value, which is normally called C minimum. I'm coming to that. This is called C minimum. Thereafter, what happens? This thing, when C minimum will happen? Just at the onset of threshold. As soon as threshold starts forming, do you know what is going to happen now? As soon as just immediately above B, when V exceeds the threshold voltage, what is going to happen? Inversion layers will now start forming appreciably. And that inversion layer will be added capacitance. So as a result, capacitance will increase. And ultimately, for very large value of gate bias, it is the inversion layer capacitance which will dominate over the depletion capacitance. Therefore, it will again reach the same value Ci from which it started. It's a very interesting curve. It starts with CVI. What is the condition of the surface at this region? Can you tell me? For V, negative values of V, what is the condition of the surface? Accumulation. There are more holes than the bulk. So as if the semiconductor, the capacitance is behaving as an ordinary parallel plate capacitance. Metal, oxide, metal. No semiconductor. The P-type, whole thing is acting as a more or less equipotential. But as soon as you go to, so it starts from, that is why the initial capacitance is Ci. The semiconductor part is absent totally. Only the insulator capacitance. For negative values of V, it is the insulator capacitance which is the total capacitance. Because the semiconductor is not playing much role. But above that 0 volt, that means as you enter into the depletion region, the CD comes in. The depletion layer capacitance comes in, which pulls down the value of the total capacitance. However, it will continue to decrease only at a certain point. That is the voltage which is nothing but the threshold voltage, beyond which inversion layer starts forming vigorously. The total charge contributed. Now you know that when I apply a voltage something where, when your apply voltage is more than Vt, this is more or less the Vt voltage, threshold voltage. This is my threshold voltage. As you come to this threshold voltage and as you exceed it, now of course there are two components of charge. One is the inversion charge, the other is, which I have just now told you. One is the inversion charge, the other is the depletion layer charge. For small values of Vg close to Vt, this Qin will still remain small. This component will dominate. However, as you go on increasing Vg, it is this component which will dominate over this. And ultimately, this will be very large compared to this. That is why this almost reaches the same value of the capacitance from which it starts. Because what is happening at the end, the electron sheet, which is just located in the interface, that behaves as a metal sheet. So the semiconductor oxide, the capacitance becomes again a parallel plate capacitance formed by the metal electrode, oxide, and the inversion layer, which is practically a metallic sheath. It is highly conducting metallic type sheath. So it becomes again a capacitance. So this plot, which can be computed using the equations which I have just now given, is called ideal CV plot. However, if you take some measurements with the help of this LCR bridge, you can do these measurements in two ways. One is normal, little bit high frequency measurement, say frequency which is of the order of a megahertz or 100 kilohertz. Then you will find your curve would be more or less, another effect I will introduce afterward. Practical curve will be in fact slightly like this, let me tell you. Practical curve will be slightly like that. But let me ignore that now. So curve will be something like this. I have ignored the interface effect. I will consider that afterward. This is what is called high frequency CV plot. It will be more or less, this region will be almost coincident with the ideal CV plot. But thereafter the rise will not take place. This rise, which is the characteristic of the ideal CV plot obtained from those equations, you will not find that rise of the CV plot beyond VTH if you take the measurement at a high frequency. High frequency typically, let me tell you, it is about 100 kilohertz. By high frequency in this case is around, say, much more than this, some criteria say about 100 kilohertz to 1 megahertz. That I am calling high frequency. Even 10 kilohertz can also be called high frequency in this case. However, if you take the same measurement at a very low frequency, say if you are doing the measurement at 500 hertz, you will get a curve, let me tell you, something like this. This may be, say, at 500 hertz. This may be at 100 kilohertz. And you ultimately take the measurement at a frequency which is, say, 5 hertz, not 500, 5 hertz. You will again a curve which is very close to the ideal curve. These are called low frequency CV plots. These are called low frequency CV plots. You see that therefore your measured results and the ideal CV plot, they differ quite considerably. The high frequency CV plot, it more or less follows the ideal curve up to the threshold voltage. Thereafter the rise does not, it becomes saturated to a minimum value. This capacitance is called C minimum. C minimum. On the other hand, if you take the measurements at lower frequencies, the curves tend to rise above from this particular point. At a frequency around 500 Hz, you may get a curve like this. Whereas when you really measure at real low frequency, almost at quasi-static condition, very little change of frequency, then you get a curve almost coincident with the ideal CV plot. But it will be shift. I am telling you two effects that I will discuss in the next class. There will be a shift horizontal as well as stretching. We shall discuss it afterward. A shift and a stretching will take place in the practical curve with respect to the theoretical curve due to the interface state effect, which we'll discuss in the next lecture. But at least if you do not, if you just ignore these effects, you'll get curves like this. Can you just tell me that why this is happening? You know that high frequency, what happens when you are applying a high, what is the source of the inversion layer for? Why inversion layer for? Who? How this inversion layer is formed? Such huge number of electrons at the inversion layer, where from it comes? From the generation recombination mechanism. Otherwise, minority carriers are so few, so many electrons can never come there. Because continuously some generation recombination process goes on. Okay? This thing goes on. But thereafter, what happens? As you are applying a, this generation recombination process is a slow process. I told you that corresponding lifetime is of the order of milliseconds. The corresponding lifetime is of the order of milliseconds.